Okay, here's a quick run through on how to draw a free body diagram. There's basically a four-step process. Step one, you're going to turn your object into a dot or a box if that's the way you want to do it. Step two is to determine if it's in equilibrium or not. Remember, if it's in equilibrium, that means it's moving at a constant velocity, it's moving at no velocity, and as a result, the forces are equal. If it is accelerating, then one, it's not in a constant velocity, and two, the sum of the forces is not zero. After you determine that, you're going to review your forces list and see which ones apply. On the forces list, you have weight, normal force, friction force, spring force, and any kind of applied force. Remember that the weight force is the only one that is a field force. All the other ones are contact forces, which means all of these must touch in order for it to be considered. All right. Also, as a side note, remember friction force acts against motion. Generally speaking, a friction force must have a surface, although air resistance is considered a special form of friction force or a special case of friction force. That just acts where wind acts against the motion of whatever you're talking about. All right, so the two samples I was going to give you tonight. The first one, step four, you're going to draw the vectors from the center of your dot or the center of your square. Okay, we're doing number 9, which is a backpack that's resting on one shoulder, just kind of like this. So it's hanging from one strap, and it says that it's at rest. If it's at rest, then we know that the sum of the forces is equal to 0. And that would also mean in this case that, that the velocity is 0. Okay, so we got our dot, and we're just going to go ahead. If it's hanging from one strap, well, actually, back up. If it's on Earth, we have the weight force, and if it's hanging from one strap, we know there's only one tension force that has to be going up. Since it's in equilibrium, they're both the same length. Now the next one we're going to do sample is number 11. Okay, so give it just a second. We're just going to go ahead, refill everything. There we go. We got just our notes up. The story is, in this case, that you have a sled is being accelerated to the right. Okay, so sled, there's a force that is accelerating the sled to the right. So if it's accelerating to the right, then we know the sum of the forces is not equal to 0, and that means it is accelerating and it's moving to the right. Okay, so draw your dot. What have I got here? Give me a second. There we go. So we draw our dot, and there, that first arrow is the force accelerating it to the right. Let's label that. Okay, so there's our force to the right, and if it's accelerating to the right, it's on snow. It doesn't say, if I recall correctly, it does not say to disregard friction, so therefore there must be friction, but that friction cannot be the same as the force because it's accelerating, so our friction has to be less than the applied force to the right. That's what it means by qualitatively. You draw vectors from the center of the dot. You want to draw them qualitatively. Or box. It's a qualitative thing, basically meaning you don't have to use numbers, but we should be able to tell if it's greater than or less than or equal. Okay, so there's those two. Because it's on Earth, we know there has to be a weight force. And since it's not moving up or down, because it's on a surface, there has to be a force balancing the weight force. And that will be our normal force. So this would be what it looks like for that one. Okay, that covers a quick how-to on free body diagrams. The end.